Let's do computer exercise number 7. It's about the percentage of students passing the math exam. We estimate the model by regressing math 10 on the log of expenditure on each student and the percentage of students in the school lunch program. The estimation equation is as follows. The coefficient on the log expenditure per student is positive because more spending on each student helps students succeed in their math exams. On the other hand, a higher percentage of students in the school lunch program implies that a higher percentage of students are from low-income families in which the support the students receive is limited. That may lead to a lower pass rate on the exam. So the coefficient on the school lunch program is negative. For the second question, it does not make sense to set the log of expenditure variable to 0. The expenditure is measured in dollars, so a 0 of the log expenditure means $1 per student. That is impossible. But it is possible to set the school lunch program participation variable to 0 because there could be schools without any students in the lunch program. If both explanatory variables are set to 0, the predicted pass rate is -20, which could not be true. For the third question, the slope coefficient on the log expenditure increases a lot in the simple regression. It is 11.16 in the simple regression, but 6.23 in the multiple regression. The estimated spending effect becomes much larger because it suffers from omitted variable bias. The correlation coefficient between the log expenditure and the school lunch program participation is negative. It is -0.927. It makes sense because the schools in rich areas tend to spend more on each student, and the families in these areas are less likely to fall below the poverty line and participate in the school lunch program. So the percentage of students in the lunch program is negatively related to the spending per student. For the fifth question, we can write down the omitted variable bias formula. The percentage of students in the lunch program has a negative effect on the math exam pass rate. The lunch program variable is also negatively correlated with the school spending on each student. That means the beta 2 hat and the delta 1 tilde are both negative. The bias is positive. The estimated coefficient on log expenditure in the simple regression is upward biased. In other words, the spending effect on the math pass rate is overstated. We can go further to verify this relationship. We regress lunch on log expenditure and obtain the slope estimate of -16.2. Then we can show that the omitted variable bias equation holds. Let's go to computer exercise number 8. We use the command summarize to obtain the sample mean and the standard deviation. The proportion is measured from 0 to 1. The income is measured in dollars. For the second question, we regress the price of soda on the black proportion and income. The estimation equation is as follows. The coefficient suggests that if the proportion of the population that is black increases by 10 percentage points, the price of soda increases by $0.0115 or 1.15 cents, holding income fixed. The effect is tiny. For the third question, we run the simple regression of the soda price on the proportion of black people. The estimated coefficient on the black proportion becomes smaller. In other words, the discrimination effect is larger when we control for income. For the fourth question, the estimation equation is as follows. If the proportion of the population that is black increases by 20 percentage points, the soda price will increase by 2.43%, holding income fixed. After the variable proportion in poverty is added to the model, the estimate of the coefficient on black proportion drops. The correlation coefficient between log income and proportion in poverty is minus 0.8385. They are highly correlated. It makes sense because higher income results in fewer families in poverty. For the last question, the statement is false. The correlation between the two explanatory variables will not cause bias in the estimates. But if one of them is omitted from the model, it will lead to omitted variable bias. Without the poverty variable, the estimated coefficient on black proportion becomes much larger because of the bias. The higher correlation mainly increases the standard error of the estimator on income and poverty, but those are not our interest. So both control variables should be included. Let's do computer exercise 9. The OLS estimation equation is as follows. The R squared is 0.0834. The R-squared in the simple regression is 0.0138. The two regressions have the same sample size. More explanatory variables lead to a higher R-squared. One more mailing per year increases the amount of gift by 2.166 Dutch guilders on average, holding other variables fixed. It is smaller than the estimate in the simple regression, which is 2.65 Dutch guilders. In the simple regression, the omitted variables as a whole have an upward bias. The response rate to mailings is between 0 and 1. The estimate is 15.359. It suggests that if the response rate increases by 10 percentage points, the gift will increase by 1.54 Dutch guilders on average, holding other factors fixed. After adding the average of past gifts to the model, we find that the estimated effect of the mailings per year drops. It is 1.201 Dutch guilders now. For the last question, we focus on the coefficient on the variable gift lost. We find that the estimate becomes negative when the average gifts variable is added to the model. When the average of past gifts is excluded from the model, there is an upward bias. That is why the estimate changes from negative to positive. We can verify the omitted variable bias equation. Delta 1 tilde is the slope estimate from the regression of the average gift on the last gift and the other two explanatory variables. It is clear why the coefficient is positive when the average gift is omitted. Let's solve computer exercise 10. The range of education is from 6 to 20. The percentage of men who completed 12th grade but not higher grade is 41.63%. The workers have higher levels of education on average than their parents. For the second question, the OLS estimation equation is as follows. Around 25% of the variation in the child's education is explained by their parents' education. The coefficient on the mother's education suggests that one more year of the mother's education leads to 0.304 more years of education for the child on average, holding the father's education fixed. We add the variable ability, and the estimation equation is as follows. The variable ability helps to explain variation in education. The R-squared rises from 0.25 to 0.43. For the fourth question, we add the quadratic form of ability to the model. The estimation equation is as follows. The first order condition for minimum education gives the ability star equal to minus 3.967. Notice that the range of ability is from -5 to +6. The second derivative is positive. The number of workers with an ability less than minus 3.967 is 15. Out of 1,230 workers, there are only 15 workers who have an ability lower than that value. It is important because the ability has a negative effect on education before that point and a positive effect on education after that point. So for most workers, the ability has a positive effect on education. For the last question, we plug in the sample means of parents' education and use the command graph two-way function to graph the curve. The ability has a positive effect on education after around -4. And then education increases at an increasing rate with ability. Let's do computer exercise 11. The dataset is about the effects of single-parent households on student math performance. For the first question, we regress math 4 on the percentage of children who are not in married couple families. The estimation equation is as follows. We can use the command summarize to find the ranges of the variables. Both are measured in percentage points. The estimate suggests that a percentage point increase in students in single-parent families leads to a 0.8 percentage point decrease in satisfaction levels in math performance. For the second question, we add the two variables to the equation. The estimation equation is as follows. The size of the coefficient on the percentage of students in single-parent households drops. The negative effect of single-parent households on students' math performance becomes smaller and not significant. The estimate from simple regression equals the estimate from multiple regression plus the bias. The bias is negative in this example, so the single-parent household effect from the simple regression is more negative than that from the multiple regression. For the third question, the sample correlation coefficient between the log of family income and the percentage of the students eligible for free lunch is minus 0.7470. It makes sense because the higher the family income, the fewer students are eligible for free lunch. The answer is no for the fourth question. The high correlation between family income and students' eligibility for free lunch will not cause the estimates to be biased. It only increases the standard error for the coefficients on those two variables. If we exclude them from the model, the estimate for the causal effect of single parenthood on math performance will suffer from omitted variable bias. For the fifth question, we need to obtain the R-squared from corresponding regressions to calculate the variance inflation factors. For the variable percentage of students from single-parent households, we regress it on the other two explanatory variables and obtain the R-squared, which is 0.8258. Then we can compute the variance inflation factor for this variable, which is 5.74. We can calculate the VIFs for the other two variables similarly. The single parenthood variable has the largest VIF, but it is still below 10, so we don't need to worry about the multicollinearity problem. It will not affect the multiple regression model we use to study the causal effect of single parenthood on math performance. Here's the 12th computer exercise. For the first question, we can summarize the variable score. The average score is 72.60. If a perfect score is defined as above 90, then 58 students received a perfect score. We use the command summarize to obtain the sample means and the standard deviations of ACT Math and ACT English. For the second question, the estimated regression is as follows. The Math ACT score is a better predictor of performance in the economics course than the English ACT score because the English ACT is not significantly different from 0 at the 10% level. For the fourth question, about 40% of the variation in the economics course scores is explained by the 3 explanatory variables in the model. Finally, we reach the last computer exercise. We will compare the estimates from simple regression and multiple regression. For the first question, we regress college GPA on PC. The intercept estimate 2.99 is the predicted average GPA for the students without PC. The OLS estimate beta 1 hat is the predicted difference in the GPA between students with PC and those without on average. In other words, the predicted GPA for the students with PC is 2.99 plus 0.17, that is 3.16 on average. The multiple regression is as follows. The coefficient on PC does not change much. It drops slightly from 0.17 from simple regression to 0.157 from multiple regression. The predicted difference in the GPA between students with PC and those without is 0.157 points on average. The beta high school GPA hat makes sense. 1 more point in high school GPA is associated with 0.447 more points in college GPA. For the third question, from the multiple regression, we find that owning a PC increases college GPA by 0.157 points, whereas having 10 more points on the ACT score raises college GPA by 0.09 points. The former's effect is larger than the latter. For the fourth question, we add the 2 binary variables for the parents being college graduates. The beta 1 hat does not change much. It drops slightly from 0.157 to 0.152. The R squared is 0.2222. The PC ownership high school GPA ACT score and whether parents are college graduates can explain 22.22% of the variation in the college GPA. For the last question, we should not drop high school GPA or ACT score because the high correlation between them will not cause OLS estimates to be biased. It mainly leads to a large standard error for the coefficients on those two variables. But we are interested in the coefficient on PC. Suppose any of these two variables are excluded from the model. In that case, the estimated coefficient on PC will suffer from omitted variable bias because high school GPA and ACT affect college GPA and are correlated with PC ownership. Thank you for solving the computer exercises with me. I hope the solutions help. See you. Thank you for watching this video and subscribing to my YouTube channel. See you next time.